This podcast is over nuclear chemistry, so we're going to study specifically the nucleus of the atom. Now, in studying the nucleus of the atom, we mainly look at the protons and neutrons. Looking at the symbol on the screen here, this is uranium. Now, uranium is an element that has multiple isotopes. An isotope would be atoms of the same element that have a different number of neutrons, which means their mass number would be different. This particular uranium has a mass number of 235, and it has an atomic number of 92, and then the elemental symbol is U. So this is typically the way that you would write an isotope when you want to specifically state what the mass number of the isotope is, which is what we need to do in nuclear chemistry. Now, when you put those symbols into an actual equation, you get what you see here on the screen. Now, nuclear reactions obviously occur in the nucleus, and one type of nuclear reaction is to take a neutron and bombard, that is like fire at quickly, bombard a nucleus with a neutron, and what that will do is it'll split up that nucleus. So you can see uranium here, and they're bombarding that uranium with a neutron, and what it will do is it'll split up that uranium and in the process produce a large amount of energy. So this particular reaction, we're producing barium as one of the products, krypton as one of the products, and then 3 neutrons as the last side product. In the process, then, an incredible amount of energy is produced. Now, you can take the masses and you can add those masses up. So on the left side, the 235 plus the 1 gives us a mass of 236. And then on the right side, 142 from barium, 91 from krypton, and then 3 from the neutrons gives us also a total of 236. So we're balancing equations much like in regular chemistry, except we're balancing the mass number, which is the top number in the symbol, and then we're also balancing the bottom value here. So if you look at the 92 total on the left, and then you add up the 3 atomic numbers on the right, you'll see a total of 92 there also. Now, using this process, we can actually figure out the symbol for a particular product. So if radium, for example, omits what is called an alpha particle, which we'll talk about here in a second, alpha particle having a mass number of 4 and an atomic number of 2, we can actually determine what the other product is. So first of all, the mass number, if the mass number of radium is 226, then the sum of the 2 on the right side also has to be 226. So that means our isotope has a molar mass of 222. We can do the same thing then with the atomic number. So the atomic number for radium is 88. And on the right side, we have an alpha particle with an atomic number of 2. We can figure out then what the atomic number of the other product is, and that is 86. And then go to the periodic table, look up 86, the atomic number, and determine that the element actually is radon with a symbol Rn. So you're balancing an equation, again, much like in chemical equations, except here you're balancing the mass number and you're balancing the atomic number. So last example here, we're going to take uranium, we're bombarding it with a neutron. We know one of the products is iodine-139, and we're making 2 neutrons, and our job is to figure out the other product. So the left side there, 236 total. So therefore on the right side, that final product must be 95, have a mass number of 95, so that the masses again add up to 236. Now the atomic numbers, again, same thing. So on the left side we have a total of 92. So on the right side there, the mass number of the missing substance must be 39, so that again we get that total 92. So we're making the 2 sides equal to each other. Then you go to the periodic table, you look up element number 39, atomic number 39, and that actually is yttrium. So the symbol there is Y for the other product. Now, in nuclear decay, there are basically 2 types of particle radiation and then 1 type of energy radiation. So we're going to take a look at the particle radiations first. And the first one is alpha decay. Alpha decay is basically a radioactive substance giving off what is equivalent to a helium nucleus. So it has a mass number of 4, and an atomic number of 2. So it's sitting there with 2 protons and 2 neutrons, and then it's stripped of all of its electrons. Now you can write an alpha particle either as He with the 4 above and the 2, or you can actually stick the symbol alpha in there and then the 4 and the 2, and you'll see it written both of these ways. Now, an alpha particle can be given off when any radioactive substance decays. So here's uranium, and it's decaying and it's giving off an alpha particle. That's the helium nucleus, and then thorium is the other product. And again, the same idea applies here. The masses have to add up on both sides, and so do the atomic numbers. Second way of writing it then is to substitute the alpha symbol in for helium. So those two reactions are exactly the same. Alpha decay typically is limited to heavy radioactive nuclei. So if you have a heavy element with a big mass number and it's radioactive, you typically will get some alpha decay. Now, the second type of beta decay we're going to get to here in a second has certain limitations as well. Now, physically speaking, here's the alpha particle being emitted from the uranium-238, and in the process, the thorium then is the other product. So here's a more visual representation of an alpha emission. Okay, so let's tackle beta decay. Beta decay is actually a little different than the alpha decay. Beta decay is actually an electron that's emitted from the nucleus when a neutron breaks down into a proton and an electron. So let me say that again. This is an electron coming out of the nucleus. Now remember, electrons typically are on the outside, but this is an electron coming from the nucleus when a neutron breaks down to form a proton and an electron. So the symbol basically for a beta particle is the symbol E. It has no mass, and it has an atomic number of -1. That's basically the charge. You can also substitute in, again, the B for beta there for a beta particle. So here's the first example of beta decay. Notice the atomic number goes up by 1 because, remember, it goes from 90 to 91 there. Remember that I said earlier that the neutron in the nucleus is splitting up to form a proton and an electron. So you actually increase the atomic number. Now the mass doesn't change because an electron coming out doesn't significantly change the mass of the element. Now here's a second example, but again substituting in the beta symbol there for the electron symbol. Now this occurs during all kinds of emissions. So it can also occur when you have a large radioactive nuclei emitting particles. And again, there at the bottom, it does, beta emission converts a neutron to a proton. And then you also form the electron, which is then given off. Now, physically speaking, here's what beta emission looks like. So you have this carbon-14, the beta particle comes out, and then you're left with nitrogen. So the atomic number again goes up by 1 because you have produced a proton in the process of emitting the beta particle. Now those are both particle emissions. The last type of radiation is gamma ray radiation, and this is just basically energy. So that last term in the equation shows you gamma radiation being given off. Notice there's no mass to it, and there's also no charge. Essentially, gamma radiation is high energy photons, and they usually accompany other forms of radiation. So if alpha particles are given off, you may get some beta. You may get some gamma, excuse me. And if beta particles are given off, you may also get some gamma rays given off. They're massless, and by themselves they don't change, again, the nucleus in any way. So the next topic is to talk about nuclear decay and radiation.